So we will take up a design problem of an RCC silo. Of course, it's an examination problem. So the data given is like this. Internal diameter of the silo, cylindrical silo is 5.5 meter. Height of cylindrical portion is 18 meter. Central opening at the bottom of the hopper bottom is 0.5 meter diameter. Grain to be stored is wheat. Unit weight of wheat is 8.5 kN per metric, that is the gamma value. Angle of internal friction is 28 degrees, that is phi value for that wheat. Angle of wall friction, actually it will vary during filling and emptying. During filling it is 0.75 times phi, where phi is 28 degree, and during emptying it is 0.6 times phi. The pressure ratio is pH by PV, as I explained in the earlier video, which is K given as 0.5 while filling, and we have to use Johnson's theory for the pressure computation, the equations which I have given in the earlier video. Materials used are M20 concrete and Fe415 steel. So we have to design the side wall as well as the hopper bottom of the silo. That means we have to find out the reinforcement required. And mainly reinforcement is this is designed as a slab wall, and the hopper bottom they are designed as slabs. So we have to assume the diameter of the bar, and we have to find the spacing of the bar. That is the design. Now let us go step by step. So here the internal diameter I am going to take it as capital D. Height I am going to take it as H. So now here what happens? I will just try to draw a single line sketch for the silo. So this is the silo portion, cylindrical portion of the silo. So wheat is stored here. So wheat is stored here. So if I take the center line of this, so your hopper bottom portion will be something like this. This is the opening. So he has given that this opening is of diameter 0.5 meter diameter, and the internal diameter of this cylindrical portion is 5.5 meter. And normally this angle is taken as 45 degrees on both sides. So since it is 45 degree, so the height of the cylindrical portion he has given 18 meters. That is given here, that is the H value, and this is the D value. And now here this becomes, so here since this 0.5 is deducted here, so this will be 2.5, this will be 2.5. 2.5 and 2.5 meter. Okay. So now this, since it is 45 degree, since this is 2.5, this also will be 2.5. So this is the preliminary dimensions of the silo. This is the cylindrical portion, and this is the hopper bottom portion. Now we have to calculate the pressures pH and PV. So the data are given like this. So what we do is we are going to calculate the pressure or whatever pressure at this level. pH I am going to take at this level, because at this level the pressure is maximum. So now if you go for the condition, actually since this wheat is a granular material, for finding horizontal pressure during emptying condition the load will be more. So I will write here, during emptying condition load is more or revolves. So that means during emptying condition it is 0.6 times phi. So you have to take the, so I will call it as phi dash, 0.6 times phi, that is 0.6 times 28 degree, which comes out to be 0.6 into 28, 16.8 degree. 16.8 degree. And we know that this phi dash is nothing but tan phi dash is nothing but mu dash. So we know I have told that in the earlier lecture that mu dash is nothing but the coefficient of friction between the stored material and the concrete wall. So you can get the value of mu dash as tan of 16.8 degrees. So tan of 16.8 degrees will be 0.3. So the value of mu dash is 0.3. Now we have to find the what is that horizontal pressure pH at this level. So for that I have to take h is equal to 18 meter, that is given. D is 5.5 meters, diameter of the cylindrical portion. Then I have to take mu dash as 0.3, and K value, of course, he has given pressure ratio 0.5. He has given that. So these are the values I need now. Now I will write the equation for getting the value of pH using Johnson's theory. So directly you can use the equation. So you have to remember this equation. So pH, horizontal pressure at this level, pH is given by, this is by Johnson's theory. pH is equal to, I will write the equation which I have given in the last class, gamma D divided by 4 mu dash. So you have to remember this equation, into 1 minus e to the power of minus 4 mu dash K by D into H. So this is the equation you have to remember. If you don't know this equation, you cannot find the pressure value. So now all the values have to substitute. Of course, your gamma is the unit weight of meter, 8.5. So gamma value is 8.5. Now let us substitute the values and simplify. So pH will be given by at this level, at the bottom of the cylindrical portion. pH is equal to gamma is 8.5 into D is 5.5 divided by 4 into mu dash is 0.3. This into 1 minus e to the power of, so we can calculate this separately and we can put that, minus 4 times mu dash K by D will be 4 into 0.3 into K is 0.5 divided by 5.5. So this value will be now 4 into 0.2, that is 1.2 multiplied by 0.5 divided by 5.5. So it comes out to be 0.109. 0.109. So that multiplied by K will be there, H will be there. So this multiplied by H, so H is into 18. So I will take into 18. So this comes out to be into 18 will be 1.96. 1.96. So you can take it as minus 1.96 then. So now let us simplify this. E to the power of minus 1.96. So that value we have to get. E to the power of minus 1.96. So I will take minus 1.96 e to the power minus 1.96. 1 minus of that, okay, this into 8.5 into 5.5 divided by 4 divided by 0.3. So you will be getting the value 33.47. 33.47. You can check the answer. 33.47. kilonewton per meter square because it is pressure. 33.47 kilonewton per meter square. You can check the value. So once this value of pH we are going to obtain, then what we have to do here is we have to calculate that tension, direct tension. We have hoop tension we have to calculate. Hoop tension, I have given the equation. Hoop tension is given by T is equal to pH into V by 2. pH into V by 2. So here B is nothing but that width. Width is nothing but here diameter. Okay. So pH is 33.47 into 5.5 divided by 2. So this value will be the value of tension in kilonewton. Kilonewton per meter, of course. 33.47 into, of course, this is 5.5 divided by 2 will be 9.654. Sorry. 33.47 into 5.5 divided by 2. 92.04 kilonewton per meter. So since it is designed as a slab, so that tension will be taken as kilonewton per meter. So we are going to now calculate the reinforcement required for this. So the reinforcement required, AST required, is given by this equation also I have given simple 1.5 times T divided by 0.87, assuming that it is under reinforced. Normally you will get under reinforced only. So 1.5 times 92.04 into 10 power 3, because we have to write in newtons, divided by 0.7 into Fe 415 Hg is given. Therefore, Fy value is 415. So you are going to get the value of AST in millimeter square. So 1.5 multiplied by 92.04 multiplied by 1000 divided by 0.87 divided by 415. So the value comes out to be 383 millimeter square. So this is the AST required. But there is a criteria for minimum reinforcement. So minimum reinforcement should be 0.3%. So minimum AST, please note that minimum AST is 0.3% of the area. 0.3% of the area. So that area of cross sectional area. Here I will take 150 mm thickness for the wall. So minimum thickness I am going to assume. So minimum thickness of wall. Minimum thickness of wall I will take 150 mm. So 150 mm thickness if I take, so AST minimum AST will be now 0.3%, it is 0.3 divided by 100 into B is 1000. I have to take 1000 into 1000 into this is 150. So if you calculate this value, so 0.3 into of course 10 into 150, it comes out to be 450 millimeter square. So you have to compare this minimum reinforcement with the reinforcement required. So here you are getting required reinforcement less, but minimum reinforcement you have to provide 450 mm square. So this is greater than required. So therefore we have to provide this much. So that is the thing. So if you are providing 450 millimeter square as the reinforcement, so you can provide torque 10, that is 10 mm diameter bars at 140 mm center to center. This you can check. So you know how to check the spacing. how to calculate the spacing by knowing by assuming the diameter of the bond. So you can go for, because the reinforcement is very small, you can go for a 10 mm diameter bond. So this is the reinforcement that is required in the wall. So that is the vertical reinforcement which is provided in the wall. So that means you are going to provide the reinforcement not 140, it is 170. So you can provide the reinforcement here. So the sketch will be something like this. This is the wall. So if you are providing reinforcement in this wall, you have to provide in both the directions. That means both along the circumference as well as vertical. So it will be something like this. See, this is how it is provided. So both these two, this one and this one, both it will be tower 10 and 170 mm center to center. So this is the reinforcement that is required in the wall.